We have seen that the homogeneous linear differential equation of the first order can be solved using separation of variables. And now what about non-homogeneous equation? One useful method to solve non-homogeneous first order differential equations is the method called variation of a parameter or variation of a constant. Two names for the same method. Let me explain this method using the following example. Consider the differential equation y derivative minus fraction 1 over 2 square root of x times y is equal to e to the power of square root of x. This is a non-homogeneous equation because it contains some expression without y. So first step, we write the homogeneous equation. Y derivative minus fraction 1 over 2 square root of x times y is equal to 0. This is a different equation, it has different solution, but it will be useful for us. To solve this homogeneous equation, we can use separation. We write y derivative is 1 over 2 square root of x y, and if we write the derivative as the ratio of differentials, dy dx 1 over 2 square root of x y, then we see that y is 0 is a solution. And second, if y is different from 0, we can divide by y and multiply by dx, and we have 1 over 2 square root of x dx. We can integrate, and we get logarithm absolute value of y, and this is square root of x plus c. Then, if we apply the exponential function to get rid of the logarithm, we have e2 square root of x plus c, which is e to c times e2 square root of x. And then we can write the solution as the constant times e2 square root of x. Apply the constant k is e to c if y is positive. The constant k is minus e to c if y is negative. And this formula contains even the case 1 when y is 0, because then k is 0. So this is the general solution to the homogeneous equation. General solution means that this formula describes all the solutions and it contains the integration constant. We have first order differential equation, we have one integration constant. For a higher order differential equations, the general solution would contain the number of constants equal to the order of the derivative. So G stands for general solution. And so this is the property of the function, of the solution. And H is the property of the equation, the homogeneous equation, the short one, with 0 on the right. And now, the method of variation of a constant or variation of a parameter means that what was constant up to now will now be a function. So we assume the solution to the non-homogeneous equation in the form that resembles the general solution to the homogeneous equation, now k be a constant. K be a function. And to stress that k is a function, not a constant, sometimes we write k bracket x close times this expression. So this is the main idea of the method of variation of a constant or variation of a parameter. This was a constant, now it's a function. So we allow k to vary, to change to depend on x. We allow it to vary, that variation, right? Making a constant be a non-constant. Well, what is it good for? Well, we need to find the unknown function k. How to do this? We take y and we substitute it here and here to the differential equation. So we have y derivative, here we have a product, so the derivative of the product is derivative of k times e2 squared of x plus, we copy k and we differentiate e2 squared of x, which is e2 squared of x times the derivative of the square root, which is 1 over 2 square root of x. This is y derivative minus this fraction, 1 over 2 square root of x, times y, and y is k e2 square root of x, equals e2 square root of x. Can we simplify this a little? Well, if you consider the second and the third term, k, exponential, exponential, fraction, fraction, the same. And we have plus and minus. So these two terms cancel each other. They annihilate each other. And this is the advantage of this method. This is not just an accident, it is always this way. So what remains is the first term, k prime x e2 squared of x plus 0 is e2 squared of x. And now we want to solve for k prime. If we divide by e2 squared of x, which we can, because this is a non-zero expression, then we have the condition for k derivative, and integrating this gives the function for k. We could write plus c. We will come to this question in a second. And when we have k, we go back here and we have y, the solution. So y is k, which is x, times e2 squared of x. And this is the particular solution to the non-homogeneous equation. And then the general solution to the non-homogeneous equation can be written as sum of particular solution to the non-homogeneous equation plus general solution to the homogeneous one. Ydn is here, x e squared of x plus, and the general solution of the homogeneous equation is here, constant times e2 squared of x. Well, not to be confused with this k, let's call this constant, say c2. 2 because not to conflict with this c. So this is the general solution to the non-homogeneous equation, to the original equation. Well, perhaps some condition. Because of the square root, x cannot be negative. And because of the fraction, x cannot be 0, so we have the domain of definition of this solution, open interval from 0 to infinity. It is easy to verify this solution if we write once again y is x squared of x, x e2 squared of x plus c2 e2 squared of x, then we can check that this solves indeed the equation. So on the left, we have y prime minus fraction 1 over 2 square root of x y. So y prime, we differentiate what we believe to be the solution. X derivative is 1 times e2 square root of x plus x e2 square root of x times derivative of the inner function, which is 1 over 2 square root of x plus c2 e2 square root of x times 1 over 2 square root of x. So this is y derivative minus 1 over 2 square root of x times y, which is x e2 square root of x plus c2 e2 square root of x. So this is on the left, and on the right we have just the exponential. So we would like to simplify this long expression to get only e2 the power of square root of x. So, well, e2 square root of x is here, so we hope 1, 2, 3, 4, we hope these 4 terms to cancel each other completely to give 0. Is it so? If we consider, well, we have everywhere e2 square root of x. So, we write this as an extra term, and then we can factor out e2 square root of x. And we have x divided by 2 square root of x plus c2 divided by 2 square root of x minus x divided by 2 square root of x minus c2 divided by 2 square root of x. And then the first term and the third one cancel each other, and the second one and the fourth one cancel each other, so this is indeed 0. So we have just e2 square root of x on the left, and on the right we have e square root of x, so what is on the left is equal to what is on the right. So this is indeed the general solution to the non-homogeneous equation.